Today you'll be learning about Op Amp integrators, accompanied by my voice and 100% royalty-free music that I pulled off some random website. So let's get into it. This is an example of an Op Amp integrator and is the example that we will be using in this presentation. As you can see, it looks like most other Op Amp configurations, the main difference being that it has a capacitor added into the feedback loop. In order to figure out what the voltage out of this Op Amp is, we have to do a couple of calculations. First, let's assume that we're dealing with an ideal Op Amp. This means that node 1 becomes a virtual ground. Node 1 is represented by E1 on the diagram. This means that the current going into the Op Amp becomes 0, making the current coming from the input equal to the current going into the capacitor. Doing nodal analysis, we can find that IC is equal to the input voltage minus the voltage at the point voltage of node 1 divided by the resistance of the resistor. Alright, now that we've got an equation going, we can take and relate the current going across the capacitor to its capacitance and the voltage of the capacitor, that is IC is equal to C multiplied by dVC over dt, and equate that to the Vn over R that we have. Now, because we know that Vc should be equal to that node 1 minus our V out, we can go ahead and plug that in there. That will give us Vn over R is equal to C multiplied by D node 1 minus V out over dt. This will give us Vn over R is equal to negative C multiplied by dV out over dt. If we rearrange our variables so that we can solve for V out, we will get dV out over dt is equal to the negative reciprocal of RC multiplied by Vn. If we integrate both sides, we can go ahead and get rid of those differentials, which will give us V out is equal to the integral of negative 1 over RC times Vn dt. Because RC is a constant, we got our negative 1 over RC is a constant, so we can go ahead and pull that out, which will give us our final equation for V out. So after I did a bit of theory, I decided to take my circuit diagram and use that to build the actual circuit. Here shown is the proof of concept circuit design from an above view. So here is our first example. In these examples, I decided to keep all of the variables the same except for the resistor. In this case, I chose a 2000 ohm resistor. For the other variables, I chose a 1 microfarad capacitor, and I also decided to put in a 5 volt sine wave input with a frequency of 1 kilohertz. So here is the simulation for that first example. This is just the example circuit to show you how it was done. And here is the graph of the output and the input of the circuit shown in the previous slide. The green wave represents the input voltage and the blue wave represents the output voltage. As we can see from our theory, this is in line with what we expected. The op amp is clearly integrating the circuit here. As you can see, we have a cosine wave for the input from this point, which gets turned into a negative sine wave, as we would expect it to do. This is the proof of concept using the NI Elvis MX suite of instruments. As you can see, our theory very nearly approximated our root mean square values and our voltage from peak to peak of our output voltage. I would say that it's sufficient enough to prove that the integrator worked in this particular instance. We will soon move to the second example where we will verify our claim and give more evidence to the idea that the integrator op amp is in fact integrating these circuits as we expected. Here is a theory for example 2. Very similar to the first example. The only difference here is that I changed the resistance to 5,000 ohms instead of 2,000 ohms. This did cause a significant difference in the value before the trig function, as you can see, and we'll see how that truly affects the circuit in a second. Although you can notice from the right side that I did go ahead and calculate the root mean square and the voltage peak to peak should be from the proof of concept. And here is the simulated circuit for our second example. This is just to show you that the only thing I changed was that resistor right there at the beginning of the circuit. And here is the graph of the second example. This makes sense given the coefficient of our trigonometric function, as there is a significant decrease in the amplitude of the output wave as we would expect. It also makes sense given the fact that we have an input sine voltage, and that input sine voltage gets turned into a cosine wave, as we would expect. Given that we're dealing with a double negative, it should go to a positive. And here's that proof of concept, just to show you that our approximated values in the theory section nearly approximated the root mean square value. I'm not quite sure what went on with the peak to peak though. There is a significant difference between the two. If you have any insights on that, please let me know.